So let's put this process to work, this outline how to evaluate a scalar line integral. So take a look here. We want to evaluate the integral of x plus y plus z ds. For c is r of t is cosine t sine t t. T runs from 0 to 3 pi. What is this? This is going to be part of a helix. We should recognize that from chapter 13, that this is part of a helix. Okay, what is going on here? Well, we already have our parametrization. R of t is already written out here, so that's great. So take a look, what do we have to do down here? We need to substitute in the parametrization to the function that we're into our integrand, take the derivative of the parametrization, take the absolute value of the derivative of the parametrization. I shouldn't say absolute value, I should say magnitude, the length, and then multiply and integrate. So, okay, let's see here. This is r of t. We know we need to compute r prime of t. So the derivative of this is negative sine t, cosine t, and 1. We know that it's not just r prime of t, I wrote here v of t, but it's the magnitude. So the magnitude here is the square root of negative sine t quantity squared plus cosine t quantity squared plus 1 squared is 1. This will be sine squared t. This will be cosine squared t. So what do we realize is happening here? That equals 1. And so we're just left with the square root of 1 plus 1. We're left with the square root of 2. So we need to throw in a factor of square root of 2 into our integral. Okay, what is our integrand now, other than the square root of 2? So this right here, x plus y plus z, is our little f of x, y, z. So f of r of t, we need to take our r of t and substitute it in here. So that's just going to be x gets replaced with cosine t. That should be a plus. Y gets replaced with sine t, and z gets replaced with t. Okay, so this is our integrand here times this, and we integrate from 0 to 3 pi. Okay, so integral over c of x plus y plus z ds is equal to the integral from a to b. And a to b is going to be from 0 to 3 pi of substitute in the parameterization into f, and so that's going to be cosine t plus sine t plus t times the magnitude of the derivative here is square root 2 dt. Okay, so this is the integral we need to compute here. Going to have square root 2 times antiderivative here will be sine t minus cosine t plus t squared over 2. Plug in t from 0 to 3 pi. And we end up with square root 2. When we plug in 3 pi here, sine of 3 pi will be 0. Minus cosine of 3 pi will be negative 1. Plus 3 pi squared over 2 will be 9 pi squared over 2. Minus when we plug in 0 here, we get 0 minus 1 plus 0 squared over 2. And if we crunch this all out, we should end up with 2 square root 2 plus 2 square root 2 plus, let's see here, this should be 9 square root 2 over 2 pi squared. So this is our first example of evaluating a scalar line integral. So what is the process here? You take your parameterization, you take the derivative, you calculate out the magnitude of the derivative, and then you take the original parameterization, not the derivative. That's a common mistake, is to substitute in the derivative into the f of x, y, z. You want to substitute in the original function the original r of t into f of x, y, z. So this times this gives you your integrand, and then you integrate. As a follow-up on this, I want to do one follow-up right here. Calculate the integral of 1 ds over c for r of t is the exact same curve here. So this is the exact same thing as here, and interpret the answer. So to do this, our f of x, y, z is just equal to 1. And we still need the same, calculations as before. I'm going to skip to the final answer. We know the magnitude of the derivative here is square root 2. And when we go ahead and plug in r of t into 1, well, that's just a constant. There's no x, y, z dependence on here, so we still get 1. So this integral is equal to we're still integrating from 0 to 3 pi of 1 times square root 2 dt, which is 3 square root 2 pi. So that was a pretty easy problem. I wasn't doing this so much to emphasize the computation here, because it's pretty straightforward. I care about the interpreting the answer here. So think about what happens when we integrate, 1 over something. It usually gives us like volume or area. In this case, we're doing a scalar line integral, and the curve is going to look like this here. And this is actually giving us the length here. So the length of this helix from 0 to 3 pi, t is running from 0 to 3 pi, the length of this helix right here, we calculate it by integrating 1 ds over this over the bounds here, and we get 3 square root 2 pi. So just to kind of summarize here, that the integral over c of 1 ds gives you the length of the curve C. Just like integrate, this makes sense, right? Integrating 1 over a region, 2D region gives you area, integrating 1 over a 3D region gives you the volume here. And also, like in this case, if C is parameterized by R of t here, then we know that this is going to equal the integral over, t is equal to t naught to t1 of 1 times the square root of, well, I shouldn't write square root here. Let me just write it. Yeah, t is equal to t naught to t1 of the magnitude of r prime of t dt. And that is exactly a formula that we should be recognizing from chapter 13. So everything ties back in together.